Welcome back, and thank you very much for coming. After the dinner yesterday, people is doing things stranger and strange this time. And the title of this talk is The Proof. A cone of spaces, each of one isomorphic two is dual, but not is conjugate dual. William Correa from the University of Sao Paulo.
Thank you. Good morning, everyone. I'd like to start thanking the organizers. It's always a good thing to come back to Badajoz. It's probably the thing I love the most in the world, except for the city I grew up. This is a joint work with Sheldon Dantas and with Daniel Rodriguez Vidanes. And as the title says, there is that cone. I'll explain it later, but let us start with a simple question, the simple observation. So start with a complex Banach space. If it is a complex Banach space, you can forget multiplication by complex scalars and consider only multiplication by real scalars. When we do that, we have X, the complex Banach space. We'll let XR be the Banach space where we forgot multiplication by complex scalars. Okay? And a simple observation, if X and Y are complex Banach spaces which are isomorphic, then, of course, when you look at the real versions of them, they must be isomorphic as well. Because you take an isomorphism and you just forget the multiplication by complex scalars, only look at multiplication by real scalars. So we define two complex Banach spaces to be real isomorphic if the real versions are real isomorphic. Okay, isomorphic by an isomorphism only with real scalars. Okay, if they are complex isomorphic, they are real isomorphic. Here's an innocent little question. If they are real isomorphic, must they be complex isomorphic? Okay. So basically, if you have the real structure of the space, can you get back the complex structure? Okay. An innocent little question. To consider it, let's look at this space, the conjugate space. Okay. So we have multiplication by complex scalars. We define a new multiplication. Now, lambda times x will be the conjugate of lambda times x. It's the same Banach space, except that we change multiplication. And of course, xr is the same as the x conjugate r. So they are always real isomorphic. And we can reframe our previous question as, is there a Banach space x which is not complex isomorphic to its conjugate dual? Okay. And just a little observation. So consider, for example, L2. It's easy to build an isomorphism between these two spaces. Just take conjugation, pointwise conjugation, because the norm is the same, right? The norm of x in L2 is the same as the norm of its conjugate. And of course, if you take any space with an unconditional basis, this here, then the same will work. And it's a surprising fact by Bourgain that there is a Banach space X which is not complex isomorphic to its conjugate dual. Okay? So the real structure of the space is not sufficient to get back the complex structure. So let me show you his space. I can't show it by a simple reason. Because Bourgain's result is exactly that. There is a Banach space. Okay? His argument is probabilistic. There is a Banach space, but I won't show you one. I show that there is a positive probability that there is one. Okay? He takes the unit ball of L2, chooses points at random, and shows that with positive probability, you get an example. Okay? So, if we want to see the example, we are in the dark. Until Carlton comes and shows you an example. So in 1995, Carlton gives you what he calls an elementary example, and it's one you can see. I can give you a formula, not for a norm, but for a quasi-norm, and that's what we'll try to work with now. So in Carlton being Carlton, it's not just an example, but it presents a connection with other parts of functional analysis. And precisely with the theory of twisted Hilbert spaces, which we have found already in this Congress. Okay. Okay. So another innocent little question. You have a Banach space. Take a subspace and look at the corresponding quotient. What have you done? You have broken apart your space in two pieces. If you look at the two pieces, what can you say about the original space? Okay? That's the philosophy behind what we call three spaces properties. So you have a Banach space, look at the subspace, and look at the corresponding quotient. Look at the properties of these two spaces, the subspace and the quotient. What can you say about the original space? So a property P is said a three-space property if whenever a subspace has P and the corresponding quotient has P, the original space has P as well. Okay? And one way to visualize that is the following. So you don't really need to know what a short exact sequence is. Just think that the middle space is the original Banach space you are interested in. Y is the subspace. And here you have X quotient Y. Okay? So a property is a three-space property if whenever Y here, the left space, and the right space have P, the middle space has P as well. Okay? So some examples. Finite dimension, obviously. If you break a space in two finite dimensional pieces, of course the middle space must be finite dimensional as well. Okay? Separability, reflexivity, and now being isomorphic to C0. Okay? Why? Imagine you have here this configuration. C0 is separable, C0 is separable. The middle space must be separable. C0 is complemented in any separable space, which is a subspace, where it is a subspace. So X must be isomorphic to the direct sum. It's again C0. Okay. So L1. You may repeat this argument because whenever L1 appears as a quotient, it must be complemented. Oh, I put L2 here, but it should be L infinity, okay? So a little mistake in my slides, but it should be L infinity. And because whenever L infinity is a subspace, it is complemented, okay? So if my slides were correct, now we should have the natural question. That is, if being isomorphic to L2 is a three-space property, okay? And as we have seen in this seminar, the answer is no. So there are spaces X which appear here in this diagram and are not Hilbertian. Okay? So any space which appears like this, it has a subspace which is isomorphic to L2 and whose quotient is also isomorphic to L2. Such a space is called a twisted Hilbert space. Okay? When X is not isomorphic to a Hilbert space. And the first example was given by Enflon, Strauss, and Pizier. By a beautiful technique, they started by considering things like that. Okay, so they made finite dimensional versions of the problem. And this space here in the middle, Fn, was at each step less and less Hilbertian. Okay? And they took the L2 direct sum. Okay? So in the end, this space must not be Hilbertian because its finite dimensional pieces are getting farther and farther away from Hilbert. But today we'll be interested in another class of examples, that those by Calton and Peck. Okay, and Calton and Peck go in another direction. So do you want to build a twisted Hilbert space? Okay, what should be the easiest way? You want to build a space X in the middle. What is the easiest one you can build? The direct sum. Okay. Take X to be the direct sum, and take this norm, the sum of the norms. So the idea was, based on previous work by Calton and Reeb, let us twist the norm. And by twist the norm, I mean this. This Y here will perturbate by some map. So we'll take a new norm here, where instead of norm of Y2, and take norm of Y minus f of X2. Okay? For F good enough, of course. You have to ensure that this will define a norm. So they show you how to construct such maps, okay? And this is their formula. So let phi be a Lipschitz map from the positive real numbers to C. And for x with a finitely supported, define this map, okay? So you are taking each coordinate, you repeat the coordinate, and apply phi to this function. It's like an entropy function. And we abbreviate that by saying that we are multiplying x by phi of minus log of modulus of x over norm of x. We can do a further abbreviation, which simplify things even more, which is phi, sorry, x phi of minus log of modulus of x. Okay, so forget the norm here. And it's understood that we are doing this calculation. So like I said, you should take f good enough so that this is a norm. If you take this kind of f, this is not a norm, but it's a quasi-norm, okay? And it defines a quasi-norm, but it is equivalent to a norm. It's possible to show. And then you take the completion of C00 times C00 with respect to this quasi-norm and define a space Z of phi. Okay? So Z of phi is formed by pairs of vectors. Okay? And we have a short exact sequence. So the inclusion there is just the inclusion in the first coordinate, as it should be. And the quotient map is the quotient of the second coordinate, as it should be. Okay? So it's possible to prove that L2 embeds here isomorphically, and the respective quotient is also isomorphic to L2. Okay, so you had all this work. It could happen that at the end of the day, this is also a Hilbertian space. So Kaut and Peck come and show you which class of maps you should take. So Z of phi is Hilbertian if and only if phi is bounded. Okay? So if you take your Lipschitz map to be unbounded, this will define to you a twisted Hilbert space. Okay? And so you are ready to show what are Kauton's examples of spaces which are not isomorphic to their complex conjugate. Okay? So you take this class of map here. Phi alpha of t is t 1 plus I alpha. So if you look at the graph, so at the end of the day, that is t times t I alpha. This is a rotation. So this is a spiral. If you take this kind of map, Kauton can show the following. If alpha is different from beta, Z of phi alpha is not isomorphic to a subspace of Z of beta, phi beta, and vice versa. So they are incomparable. And the complex conjugate of Z of phi alpha is isomorphic to V of Z of phi minus alpha. Okay? It makes complex sense. You are taking the conjugate here. Okay? If you look at the norm, look at this map. You try to reproduce this map. What you have? Norm of yx in Z of phi alpha conjugate should be the norm of y minus x conjugate phi minus log of modulus of x conjugate 2 plus norm of x2 conjugate. Okay? Like I said, the norm of x conjugate is the same as the norm of x, so this appears. The modulus of x conjugate is the same. We have here a y conjugate, x conjugate. Take the conjugates here and put here. Okay? So it will conjugate the alpha there. So in particular, if alpha is different from 0, this space is not isomorphic to its complex conjugate. What about alpha equals 0? Okay? Because, of course, this only works for alpha different of 0. And for alpha equals to 0, sorry, it should be alpha here. We have that the map is phi 0 of t equals t, and you get the Kauton-Peck space, which has already appeared a number of times here. Okay, and it is an extreme example. So Q is a strictly singular map, which means that it's not, when you restrict to an infinite dimensional subspace, it's never an isomorphism into its image, and I is strictly cosingular. So don't bother a lot about this. It comes from, because I is the adjoint of a strict singular map. Okay? But the real property that will make it interesting to us here is that it appears as the derived space of this interpolation couple. So we have two links already, real versus complex isomorphisms, twisted Hilbert spaces, and now appears the third link, complex interpolation and derived spaces. And again, it has already appeared a number of times here, but to remember is to live, right? So remembering, the goal of the interpolation theory is the following. You have an operator that goes from x0 to y0, and the same operator goes from x1 to y1. You want to find spaces xy so that you have this implication, okay? So continuity here and here implies continuity here. And the classical example is the restoring theorem, which I have put in a simple form here, but it says that if T is a bounded operator on L infinity, which is also bounded on L1, then it's bounded on every LP space. Okay? And its proof inspires the definition of an interpolation method. That is a method to define these spaces, x and y. It inspires the definition of the complex method of interpolation. So the idea is simple. Where I put it? Here. So define the strip on the complex plane of numbers with real part between 0 and 1. And you have a couple of spaces which you want to interpolate, okay? And you consider a space of analytic functions defined on this strip. And they go to the sum space, which is a space that contains both x0 and x1. And among many properties that you want this space, the functions in this space you have, you want that the points here take you to x0, and the points here take you to x1. Okay? And whatever appears in the middle, so this is theta, what appears in the middle will define your space x theta. Okay? So x theta is defined as the image of theta by the functions in f, okay? With the quotient norm. And the classical example, you take the couple L infinity L1, interpolate, you get the LP spaces. And of course, you have an interpolation theorem. If T goes from x0 to y0 and from x1 to y1, you have automatic boundedness in the complex interpolation spaces. Okay, so another innocent little question. You are dealing with analytic functions. What if you consider the derivatives? So now define the derived space, where you don't look only at the image of the functions, but at the image of the derivatives, and put on it the quotient norm. So you get a short exact sequence. Okay? So you can prove that if you include in the first coordinate here, you get a subspace isometric to x theta, and the respective quotient is also isometric to x theta. Okay? So if somehow you got here the interpolation space to be L2, you get a factory of twisted Hilbert spaces. So the example, L infinity L1 at 1/2 gives you L2, and the derived space is the Carlton-Peck space. And more generally, we had those twisted Hilbert spaces coming from Lipschitz maps. If our phi here is real valued, then you find an Orlick sequence spaces, which when you interpolate with its dual at 1/2, it gives you L2, and the derived space is precisely this one, up to isomorphism. Okay? So if the image here is real, all those spaces defined by Carlton-Peck come from complex interpolation, from the derivation process. Okay? But remember Carlton's example. It was T to 1 plus I alpha. This is not complex. Sorry, this is not real. This is complex. So you are not in the case of couples. So what's happening? Okay? So all of these links, so real versus complex isomorphism, twisted Hilbert spaces, and complex interpolation and the derivation process. So you have all these things together working somehow. So this leads you to some basic questions. First, recall that the Carlton-Peck space has that extreme behavior. The quotient map is strictly singular. So the question is, why? Why does it have this extreme behavior? And how rare is that behavior? The second question. So Carlton somehow is able to distinguish between his examples. All the examples appears in a diagram of this sort. All these spaces are very close to being Hilbertian. It's very difficult to distinguish between these examples. So Carlton has done some kind of miracle there. So it's interesting to understand what he has done to see if we can replicate that. And third, so this space is not isomorphic to its complex conjugate if you take this kind of maps. Is there any relationship with complex interpolation there? So these are the kinds of questions we were thinking about in this work. So the first question, singularity. Why does E2 has that extreme behavior? Why does the Carlton-Peck space has a strictly singular quotient map? Okay? And how rare is that behavior? So let us say that the twisted Hilbert space is singular if the quotient map is strictly singular. And a little bit of history. There might be some gaps here, but it's only because of my ignorance. So if anyone knows more, please tell me later. So when Carlton and Peck defined their examples, Z2 was the only example known of singular twisted Hilbert space. Then come Castillo, Ferenczi, and Gonzalez and present some more examples. Okay? So if you take the Tissirson space, interpolate with its dual, at 1/2 you get L2. And the derived space is also a singular twisted Hilbert space. And they get some more examples, for example, considering Z of phi alpha. The spaces Carlton showed to be counterexamples. Because phi is what they call an expansive map. Okay? And Suarez recently gave new examples through convexification, and in particular, if you take the two convexified Tissirson space, the derived space is also singular. So our result. Let phi be a B-Lipschitz map. Okay. So if you look at Z phi, it is defined as pairs of vectors, right? Sorry. Here you find a basis. Okay? You have a basis formed by these vectors, En 0, 0, En. So this is never an unconditional basis, okay? Unless Z phi is Hilbertian. Now, if phi is B-Lipschitz, and if you take n normalized basic sequence, it has a subsequence equivalent either to the canonical basis of L2, which comes from here, from the first coordinate, or from this Orlik space here, which comes from the second coordinate. So if you take a vector of this form, 0, x, in Z of phi, what is its quasi-norm? It will be the norm of x phi of minus log of modulus of x, 2 plus norm of x2. But if phi is by Lipschitz, this behaves itself as like this, x log of x. Okay. So that's where you get this Orlik sequence space here. So you may show that actually every normalized base sequence has a subsequence equivalent to one of these. In particular, if you take your basic sequence to be UN Vn, and the second coordinate is far from 0, you must be in this case. Okay? You must be in the case of the Orlik sequence space. And this implies that the quotient map is strictly singular. Okay? Because if it was an isomorphism between an infinite dimensional subspace here, you should get that the second coordinate is bigger than 0. And you should be in the case of the Orlik sequence space, you would get that L2 is isomorphic to this Orlik sequence space. Okay? But this was already implied by expansiveness, the result I mentioned by Castillo, Ferenczi, and Gonzalez. Okay, so the real content here are these two things, that you get only two normalized, two subsequences, two classes of spaces there. Okay, so this kind of answers the first question, why singularity? Now the second one, how can we distinguish between the examples? Because like I said, these spaces are very similar to each other. So we entered in the proof of Carlton that the spaces are different. And we were able to see what really is used there. Okay, so these are the properties that are used. So your map must be by Lipschitz. And they say that phi lies in these L bits if the second derivative exists and goes to 0 as t goes to infinity. And we have this property here. Okay, that's a technical one. There is no escape, because when you go to Carlton's proof, the idea is beautiful, but unfortunately, it's buried in a mountain of calculations that you have to understand. So this is our result. If phi and psi are in this set of functions that I defined here, and we have this condition that they are far apart. So for those who know the terminology, this means that the quasi-linear maps are not projectively equivalent, then the twisted Hilbert spaces are incomparable. Okay? So, and the idea of the proof is the following. Okay, so the vectors here in my z of phi, like I said, are pairs of vectors in of sequences. Okay? If they're pairs of sequences, you could consider operators of this form, matrices. Okay, so just apply lambda mi at a sigma to ix, matrix multiplication. So if you do the calculations, you choose some vectors, you can show that if an operator is bounded from z phi to z psi, this sigma must be 0. Okay? So suppose that S is an isomorphism into its image. So remember that the first coordinate here defines a subspace isomorphic to L2. Okay? It follows that when you take S, the image must be essentially contained in the L2 of the second space, okay, which is the first coordinate as well. By essentially contained, I mean that the second coordinate of the image must go to 0 along the basis. From that, it follows that if you look at the second coordinate here, which is isomorphic to that Orlick sequence space, when you apply S, the second coordinate of the image must really be used. And by that I mean that the second coordinate must not go to 0. Okay? And from that, okay, so if your spaces had unconditional basis, so suppose you have an operator from x to y, you could represent it by an infinite dimensional matrix. Okay? 1, 1, 1, 2, 1, 3, and so forth. Okay? If the spaces had unconditional basis, there is a result that says that from that, you get that this operator here, the diagonal one, is also bounded. Okay? But your spaces do not have an unconditional basis, but they have what we call an unconditional finite dimensional decomposition. Okay? Because remember, this is a basis that is not an unconditional one. But if you pair two vectors, so define En should be the span of these two. This defines a two-dimensional unconditional decomposition. And then here, you substitute this by matrices, by 2 per 2, by 2 matrices. Okay? And you have that the diagonal matrix here is also bounded. Okay? And since by the third step, the second coordinate really must be used, so this is a matrix, so lambda 1, mu1, eta 1, sigma 1, and so forth. This sigma 1 here must not go to 0. Okay? So you get to a subsequence, you get a matrix of this form that is bounded on the spaces, and you get a contradiction. But of course, okay. So we know how to differentiate between examples. But of course, now I must show you examples. Okay. So remember the first question, it was why the quotient map is strictly singular and how rare is that behavior. Okay, so I got a lot of examples. In particular, I got a whole structure of examples here. Okay, so let us say that a set is coneable if it has an infinite dimensional cone inside of it. And I got a family of examples of functions of that kind that form an infinite dimensional cone. Okay, so you want Lipschitz map, you take the identity and perturbate it by something. Okay, and this something here is chosen so that those other properties that I want are valid. Okay, remember this little monster here. Okay. So these form an infinite dimensional cone inside L bits. It must be a cone. It cannot be a subspace, because if you take G beta and subtract from another G beta, this X here will cancel, and you'll lose by Lipschitz. Okay. So this set here forms an infinite dimensional cone, and in particular, the set of bi-Lipschitz maps is coneable as well. Okay, and so how rare is singularity? Well, you actually get an infinite dimensional cone of spaces with singular quotient map. By that I mean you have a cone of bi-Lipschitz maps such that the corresponding twisted Hilbert space is singular, and you can differentiate between them. Okay, so if phi and psi are not multiple one of the other, then z of phi is incomparable to z of psi. So this kind of answers the first and the second question. And there is the third one. What's the connection with complex interpolation? Okay. So what's the connection between being non-isomorphic to its complex conjugate and complex interpolation for the spaces z phi? So a fact, if you do the calculation I did at beginner for the maps phi of alpha and replace them, you get, take phi and psi to be real ones, takes phi plus I psi. The conjugate space is z of phi minus I psi. Okay. And from that you get a cone of examples of spaces which are isomorphic to their dual, but not to their conjugate dual. Okay. So as we'll see, every one of those spaces that we are considering, they are isomorphic to their dual. Okay. But this kind of example, with considering complex maps, they will not be isomorphic to their conjugate dual. So we get a whole lot of examples, and they are explicit. We can look at them. And here's the last part, the connection with complex interpolation. Each one of these spaces is defined by complex interpolation, not of a pair, but of 4 spaces. Here's an image that helps explain why these spaces are isomorphic to their dual, but not their conjugate dual. Okay? So this is based on the paper, The Butterfly Lemma, by Jesus Castillo and Daniel Morales. So they show the following. Suppose that z of phi is defined as the derived space of this couple, X and X dual. And z of psi is defined as the derived space of this one, Y and Y dual. So you want to know what defines the space z of phi plus I psi. They show that you must go to interpolation of 4 spaces. Okay. So the idea is the same. You had 2 spaces, you want to get automatic boundedness of some family of spaces. Now you have 4 spaces. Okay. So the idea that you had before one space here and one space here. Now you have a family of spaces on the unit circle. Okay. So consider this configuration. X, Y, Y dual, X dual. The derived space they showed is z of phi plus I psi. Okay. While, if you want to look at the dual, this should be plus here. They also show that the dual is defined by this configuration, X dual, Y dual, Y X. But look at both of them. This one is obtained from this one by rotation. Okay. So let us call the first configuration Z. You have the space of analytic functions associated to the first configuration. Let us call the second one z-dual. There is a simple way to get functions from here to here. You take f of z and send to the rotation, f of minus z. Okay? So this defines an isometry between these spaces. And remember that the derived spaces were defined as quotient spaces of these ones. So the derived spaces are isometric. This explains why the dual of the space is isomorphic to itself. But if you look at the conjugate space, now you want to get phi minus I psi. And they show that this is the configuration, okay? So this is the original one, this is the new configuration. How do you obtain one from the other? So here is x, here is x. Here's y, here's y dual. Here's y dual, y, and x dual, x. So up to our rotation, what you did was conjugation. So we wanted to go from here. So let us call this configuration z bar. You want to go from f of z to f of z conjugate. But this is not an analytic function. Okay? So you lost the isometry. So that's a visual manner to see why, from complex interpolation, these spaces cannot be isomorphic to their conjugate. So, okay, we got a lot of examples. We have an infinite dimensional cone of bi-Lipschitz maps such that when you look at the induced twisted Hilbert space, the quotient is strictly singular, the inclusion is strictly co-singular, each one is isomorphic to its dual, Z of I has all the properties a twisted Hilbert space has, so it's reflexive, it's L2 saturated, it has arbitrary type and cotype not 2, so it's really close to being L2. Every normalized base sequence here has a subsequence equivalent to the canonical basis of L2 or of L2 to square log 2 square of t. And also we have another representation as a twisted sum. So remember you had L2, Z of I, L2. This came from considering inclusion in the first coordinate. If you consider inclusion in the second coordinate, you get you get the Orlick space, and the quotient is the dual of the Orlick space. And by miracle, we can distinguish between all of these spaces. All of those properties from the beginning are properties of the Carlton-Peck space. So there are plenty of fish in the sea. But there should be only one Carlton-Peck space. It's not a question of, is the Carlton-Peck space special? The question is, why is it special? Okay? One never forgets its first love. It might be for really bad reasons, but one never forgets. So Carlton-Peck is our first love. So I would like to finish with an open problem, which is trying to give a characterization of the Carlton-Peck space. So this is a characterization of the LP spaces and of C0. So if you take a Banach space with a normalized basis, which is equivalent to all of its block basic sequences, it must be either C0 or LP, for finite P. Okay, so I said that the Carlton-Peck space is the derived space of L infinity L1, but it's also C0 L1. You could change here to C0. So here's my question / conjecture, which I learned this week is also from Felix Cabello. So suppose you have a phi, a Lipschitz map, a bi-Lipschitz map, and you take blocks from L2. So UN is a sequence of blocks from L2. And consider this subspace here. Sorry, consider this sequence of blocks inside the space Z phi. In the Carlton-Peck space, this sequence is equivalent to the original one. So you get a subspace isomorphic to the Carlton-Peck space inside of it. So is the Carlton-Peck space the only twisted Hilbert space that does it? So this is the open question, trying to understand why is the Carlton-Peck space special. It is special. You just need to understand better why. Thank you very much.
Okay, So if I get you right, nothing of what you told us is real.
Yeah.
Questions or remarks? Just one. Can you come back to the first question slide?
Yes. This one.
There. The next one. Yeah, there. Are you aware that what you say move on to the higher order Rockberry spaces?
Yeah. I have no idea what happens there. It should happen. Yeah.
Is there? You have n type of basic sequences, the conjugate stuff, everything. Which spaces is not more complicated. I mean, you have it there. Any more questions?
Hi. Have you looked at the function space versions of Galton Peck space? I mean, interpolate capital L, L infinity and capital L1, and then you have singularity, but you also have disjoint singularity, right? Which is, I don't remember if it's stronger or weaker, but weaker.
Weaker, yes.
I mean,
no, I have not looked at that.
No.
I suppose it should work as well, but
Yeah.
I have not looked at it.
I don't even know if Galton's example would make sense.
Okay.
Oh, well, then, well, okay. So,
No. I suppose it makes sense as well, but I have not done the calculations.
yeah. Okay. Thank you.
You're welcome.
He's lying. He knows everything there is about the big Galton Peck spaces.
Yeah.
Anything else?
So there is a beautiful result of Wozanovsky. So if you interpolate by complex method with parameter 1/2 any Banach function lattice on a given measure space with the Kette dual, so we get isometrically L2 in
Yes.
this measure space. So then if you take some complicated Banach lattices and apply this procedure, then this probably will give something also new.
Yes, I mentioned the work here. Where? So this one, by Castillo, Ferente, and Gonzalez, was about that. Was about look at the interpolation of a space with its dual. More generally, of two spaces. You want that the two spaces that you are interpolating, are in some sense far apart from each other. Okay, they have very different properties. So the the twisted Hilbert space that you get at the middle should be singular. That's the idea behind of it.
Good. Any other question? Okay, then we will make a break at 11:30, coffee break, and let's thank the speaker again.
Thank you very much, Jesus. And thank you very much to all organizers of this wonderful meeting. Badajoz has something special, and I will explain why. The first time that I came here was a conference, a seminar in 1 week by two professors. One of them was Hoverland, and the other one was Manuel Valdivia. When I see Manuel Valdivia speaking mathematics in the blackboard, I thought. I never seen something of the same matter, of the same spirit, of the same way in my university. I'm sorry, but reality is reality. And Valdivia was another level. Then was for me so convinced that I went to visit him. I didn't know him, but I went to visit him in order to ask him to direct my thesis. He agreed with me, not before putting me to study the Kete 2 volumes for 1 year. And after that, then he was director of the thesis. So this was in Badajoz. The second time is another meeting organized by the people here, by Jesus and Felix, all of you, Rodrigo, was a meeting in Cáceres. And there was a wonderful talk by Argyros. And in the audience was our friend Richard Haydn. In this talk, but hereditary in decomposable spaces, Haydn asked if it should be possible to introduce Delbine L-infinity construction, Purgen Delbine, L-infinity construction, in the things that he was doing. 2 years later, the result was a wonderful paper without C of K, without operators. So, and this happened here in Badajoz too, okay? So for me, it's a real pleasure to be here, and let's see what happened this time. We need some time to see what happened, but I'm pretty sure that something will happen. And thank you very much again for this invitation to talk here this time. Anyway, I'm going to, I'm a non-separable man. I normally work in non-separable Banach spaces. And there is some kind of conflict between people in separable Banach spaces and people in non-separable Banach spaces. The conflict means that some of the non-separable Banach spaces, some of the separable Banach spaces specialists doesn't like to much go behind the continuum, right? So, no doubt there is a problem with the set theory, as we are seeing in the conference, but it's always possible to restrict a little bit ourselves in order not to get to use the axiom so much. I'm not going to use any axioms. I'm going to solve one problem, which is a long, long-standing open problem. And it's a problem of Lindenstrauss. The problem of Lindenstrauss is the problem 18 in a big paper that appears as conference in Paris in 1977. And the problem, I will explain later, was characterized Banach spaces that admits an equivalent strictly convex norm. A strictly convex norm. What means strictly convex? What means strictly convex? A strictly convex means if this is the ball, if this is 1 point, the line segment is not in the ball, only contains the point. There is no line segments in the unit sphere. This is a strict convexity. A strict convexity is related with Gateau differentiability by the duality. And there is another concept which is this is stricter convexity, rotundity, and there is another concept which is locally uniformly rotundity. Locally uniformly rotundity, everybody remember, this is the parallelogram identity, right? In Hilbert spaces. Pythagoras theorem. So let me put this here with the minus ones and say this equal 1. So parallelogram inequality is again the same. Is this. Strict convexity means that when this is 0, x must be equal to y. This is the definition of the strict convexity. It means exactly what I said before. And locally uniformly rotundity means that if I wrote here xn plus y, xn plus y, xn minus y, then the thing that happens is that this must go to 0. So locally uniformly rotundity at the point y means this, that the parallelogram law holds asymptotically at that point. So that's the meaning of locally uniformly rotundity. This is related with Gateau differentiability, and this is related with FECHA. Okay? By duality. In the sense that dual, this convexity property implies a pre-dual norm is FECHA or Gateau, whatever. Bien. Then the thing that I'm going to talk is about these two concepts, rotund and locally uniformly rotund. And the problem of not, okay, sorry because of that, okay. The problem is, as I tell you, was Lindenstrauss was characterized when this happens. The thing that happened is that has been easier to find characterization of this. And we work a lot finding characterization of this. For instance, I remember Gilles Lancien, when you showed that in spaces with Radon-Nikodym property, in which the derivation index is less than omega 1, then you have Lure normability. For instance, this is Lancien. So this has been strongly attacked. For this, I know less. But the first papers of Lindenstrauss was to construct in a reflexive Banach space, to construct a rotund norm. And he did it because he constructed an operator 1 to 1 to C0. And this norm on C0 is strict convexity. So you transfer from C0 to the space reflexive strict convexity. And this is the thing that Lindenstrauss did. Later on, the genius of Trojansky was able to find LUR there too, locally uniformly rotundity too. Okay, so I'm saying all these things because I normally works in the non-separable context, looking for this kind of renormings. And going to say the result. The result is, I'm sorry to say, but if nobody says, I will say. But this time I will say the first one. The result is absolutely wonderful. The Banach space admits a strictly convex norm if, in only if, in only if, there is another one with separable faces. That's all. So, it's necessary to glue a ball with separable faces. A polyhedral with separable faces. This is a strict convexity. If and only if. That's geometry, that's topology, and that's everything. Because it's the answer that Lindenstrauss was looking for. It's not possible to ask him. But I say here today that this is the answer that Lindenstrauss was looking for when he asked it, because of the way he asked the question that I'm going to write here now. Okay? What about locally uniformly rotund? The main concept in a LUR space, in a LUR norm, is the concept of dentability. Gilles, dentability. You have slices of diameter less than epsilon. One point is dentable. If you take an epsilon, you take the ball around the point, you eat the ball, you take the complementary, you make the convex curl of the complementary, and you don't teach the point. You have not the point. So there is a slice, verify this. So dentability is the other concept which is inside here. Theorem. The Banach space admits an equivalent locally uniformly rotund norm if, in only if, in only if, it has another one with separable and denting faces. Gilles, separable and denting faces is the same as LUR, and separable faces is the same as rotundity. I'm sorry, but this is wonderful. And many years working on renormings, many years working on renormings. And I didn't suspect that. Okay? But anyway, I think that is enough to introduce the talk that now I'm going to pass in order that these ideas will be clear enough. Okay? So, but these are the two main theorems, the two main ingredients of this. Of course, there is a lot of new cases. New cases. For instance, with Haydn and Molteau, we show with the C of K for K Rosenthal compact separable Rosenthal compact such that the point of functions admits countable many discontinuities at most, the C of k is Lure normable. Now, I know this for k non-separable. We asked it in the paper. Richard Haydn, Molto, myself asked it in the paper. Because we only knew fragmentability of the space. But we didn't knew renorming. Renorming we knew in the case of separable Rosenthal compacta. And there are other cases of new results, okay? So, the context is solution to Molto-Trojansky-Valdivia questions, solutions to Haydn-Molto questions. We are going to talk about Jordan content and Howard measures, because here we are working with the diameter. The diameter certainly is a way to measure the size of the set. But there is another measure of sizes. Jordan content, Hausdorff measure are different than the diameter. And with all of them, we are going to have theorems. Even with slicing with non-separable index small enough, which is the separability assumption that I'm saying. So at the end, we shall construct Lure norms by pressing down separable faces. This is very funny. I mean, imagine a football ball. Imagine the pentagons of the football ball, okay? These are the faces. The theorem says that if you press a little bit on the face and you don't get any point of the disjoint faces, the other one, then the space is Lure normable. I have a polyhedron, okay? I press on the faces. If the pressing of the faces doesn't add contact to any other face of the polyhedron, I have Lure. This is another wonderful thing which was never said before, because nobody, all we were looking outside. And now it's saying press. If you press and don't touch the other faces, then you have Lure normability. So at the end, I have the solution to the industrial problem and the solution to other problem of Richard Smith, who has a problem related with if dual state convexity is a topological property. Because we, with him and Trojansky, proved that it was so for C of k. Later, he did, just 2 years ago, 2 years ago, he did for Asplund spaces. Now the answer is yes in general. So any Banach space, you go on the dual space. If you have an homeomorphism for the weak star topology, it preserves dual state convexity. So, dual state convexity is a topological property of the weak star topology. It's as simple as that. Okay? So, and this is the solution to a question of Richard Smith that I'm following to use Here is our 224 average price Mr. Talagram, and I put there because a lot of things that has been developed in Banach space theory began with him. And last month, he received the average prize. And nobody says nothing. Average prize is Nobel Prize. Average prize is Nobel Prize in mathematics. It's the Norwegian Academy of Science. And they gave to Talagram. Mr. Talagram was the first one to begin because Choquet was the director of his thesis. And he did a paper, Weekly Key Analytic Banach Spaces, published in Annals. How many of you have a paper in Annals? I'm sorry to say. Annals. I've been talking with mathematicians that have been criticizing the paper and the figure. But the people who criticize this has not any annals paper. Weekly K-analytic Banach spaces in Annals of Mathematics 1999. Why this is related? Why this is related with myself, at least? Because of the very beginning. Of the very beginning. The things are explained very easily if you go to the very beginning. Then this is the very beginning. Grothendieck another one which is about mathematicians, Grothendieck, proved that CP of K for K compact is angelic. Angelic means that all concepts of compactness coincide. Countably compactness, sequentially compactness. And even more than points in the closure are limit of sequences. These things that we are using every time that we have an integral because we need to apply Lebesgue theorem. So there are two remarkable properties. They call somebody, I don't know who, say angelic. Many people asked me, what angelic? I really don't know. But they call angelic because of something. So CP of K is angelic space for a compact space. For a compact space, this is a Smulian Banach spaces, but this is Grothendieck, CP of K. I have the opportunity to do this in CP of X for X, a K-analytic space. The K-analytic space was the space used in Talagram paper. I was a student. I wrote the theorem. I sent to see my advisor in Murphy. And my advisor said, okay, Orihuela, you have this, but go to Talagram paper and read it carefully, because if you did it, Talagram must have written it down. My advisor in Murcia to me. What I did, I went outside of Murcia to do the thesis, of course. I did it with Valdivia, fortunately for me. But anyway, the theorem is not inside. It's not inside. The theorem is a new theorem. And is related with Burgen-Fremlin-Talagram, another three, which are bad mathematicians. That the bare one functions of the first bare class on a Polish space is an angelic space too. So these are the three results on angelicity that are related with my work and are related with K-analytic, with descriptive, and with Talagram. Co-authors of the things that I'm saying this is the list of papers, so I don't bother you too much with these things. Anyway, there are things which are preprints with Montesinos that will be appear. One is going to appear in PAFA, and the other one is going to appear soon too, I imagine. Okay. The definition of locally uniformly rotundity. So, is as I said, and the important thing is to analyze this, quadratic form, okay? The main result. A Banach space. Another thing is that if I'm renorming a space, nothing happened. But if I'm renorming a dual space, then I like to know if the norm is dual. To be dual norm is to be weak star lower semi-continuous. So in order to have full generality in results, I always write E, F, and F is a subspace of the dual, and I'm going to look for these norms, but lower semi-continuous with respect to the pointwise topology over this set F, fixed from the very beginning. This is a technicality, okay? But the theorems are they are with this. Okay. So I have a Lure norm. I'm not going to say any more about this F, okay? You understand that this the size and the dual is the same. It's written down, but in the way of speaking, I prefer not to say any more. And I simply say that the theorem says that we have a Lure norm if and only if there is a sequence of subsets AP such that every point find an slice here in which the point is, and these can be covered by countably many balls of diameter less than epsilon. So it's an approach in which the size of the half space of the slice is measured not with diameter, with countably many sets of this diameter. A finite is Kuratowski index of non-compactness is the distance to a finite set. Here is the distance to a separable set. If the slice distance to a separable subspace is less than epsilon, the space is Lure. Esto es magia. I'm sorry to say, but es un milagro. Okay? This renorming can be achieved as soon as this happens, and this slice is inside ball epsilon plus something, and something a separable subset, in particular a space with finite Hausdorff measure. All spaces with finite Hausdorff measure are separable, all of them. So this is a very strong result. I began to work with house door measure, but later I realized that separability is the only thing that we need. This result completely solves 4 problems asked by Molto, Trojansky, Valdivia, and myself. Generalized Trojansky fundamental result, which is wiped down in chapter 4 in the Wilger de Froid-Fiedler book. Molto, Trojansky, and myself theorem in Lure normis is also contained here. Lancien and Raja approach for that is also included here, as well as Garcia, Oncina, Trojansky, and myself, where finite covers were considered too. We indeed consider finite balls, number finite of balls. Banach spaces C of K, where K is a Rosenthal compact. A Rosenthal compact, remember, is a compact space of Berg-1 functions on a Polish space gamma, with at most countably many discontinuity points for every point of the compact. This is also Lure-normable, and this solves question of Haydn, Molto, and myself, because we did it for separable space only. So this is the thing that we have. In order to get a feeling of the way of proving, let me remember the definition of the network. Network is a family of sets which is as the basis of neighborhoods, but the sets are not necessary to be open. This is a network. And Banach space is Lure-normable if and only if it has these things, but these things with here the diameter instead of countably many. The first theorem was this one. Okay? Jordan content. Well, Jordan content, as you say, is something which is covered by a finite number of sets of diameter less than delta, with delta finite Jordan content. So this is possible to apply here. Dimensional Hausdorff measure the same, but now we need to add a series. And there is a function alpha, and they say alpha dimensional Hausdorff measures because of the function that you use. But essentially, you always have coverings. You always have coverings of my set with countably many sets of diameter less than something, which is enough for the thing that I'm doing. Well, this is the definition of the Hausdorff measure. I'm not going to enter in the details, but anyway, is because the theorem that I did first for that, this is why I wrote. But okay, is for separable is better. So how to attack these theorems? How to make a proof? Which is the idea? The idea is the following. I'm going to have one set. And after, I'm going to have a family of closed convex subsets. The family of closed convex subsets will be given by an hyperplane and the complementary of the hyperplane. A half space. So I'm going to have half spaces here. Half spaces. So the theta y closed convex half spaces here. Then I quantify the localization of points in these sets through a LUGAR condition on a quasi-norm, on a norm. Okay, if I have, I can construct a norm, lowest norm, such that this is the LUGAR condition, this is the quadratic, this is the LUGAR condition. Imply that there exists some n such that x is in here, and also the xn are in there. So dx and xn in my dx and xn in my sequence, looking for the renorming, in my sequence, the x, if it's x here, xn is also there. There is a sequence of sets, there is a sequence yn such that if x is, xn is also. Eventually, okay? But this is much more than enough, because if these sets are small, diameter less than epsilon, then the distance is small, so I have the renorming. But if these sets are covered by comfortably many sets of diameter less than epsilon, I can refine the construction in order to get the same thing. So it's possible to control all time the matter, which simply means that this is the way to renorm. This is the way to renorm. Until now was not possible to do that. Okay. Open localization and approximation. In this situation, the thing that happened is that I'm able, for a given sequence that verifies the LUGAR condition, then I have a sequence of indices in which both x and xn are, and even more. If the xn are not in A, if xn are not in A from the very beginning, it doesn't matter. If x is in A, it's important. For instance, if x is in the sphere, it's important. But the xn doesn't matter because I'm going to have this formula of approximation. If the convex hull of a small set is small, plus a ball is small. So the distance between xn and x is small. And we have LUGAR. And in the case of a strict convexity, we have x equal y. Because it's the same. Okay? So, this is the delta. Okay, this is the statement. The following are equivalent. It admits a lower semi-continuous LUGAR norm. There is a sequence of balls centers in 0 with rational radius, and H the family of open half spaces. Then the family of the slices of the balls is a network for the norm topology. This is the sequence could be chosen, closed, convex, arbitrary, and then the difference is a network for the norm topology. Have a look here, topologists, have a look here. The network is formed by sets which are difference of closed sets, closed convex sets. This is an important thing too. Anyway, there is a sequence of subsets such that this family in general is a network. So this is so let's now go to the question of Lindenstrauss. Characterize those Banach spaces which have an equivalent strictly convex norm. He didn't ask anything about LUGAR. Strictly convex. In the words of Lindenstrauss, it is easily verified that every separable Banach space has a strictly convex norm. The same is true for a general weakly compactly generated spaces. They did, with the resolution of the identity. On the other hand, it was shown by day that there exist Banach spaces which do not have equivalent strictly convex norm. Some conjectures concerning a possible answer to the question were shown to be false by Dassel and Lindenstrauss. There are examples, they look for positive results and they couldn't do it. These results show that even for C or K spaces, it seems to be a delicate and presumably difficult question to decide under which conditions there exists an equivalent strictly convex norm. So it was the feeling of Lindenstrauss about the matter. Probably this is the reason why until now has not been able to obtain the answer. So the answer is the one that I said and another one that we obtained before with Smith and Trojansky, which is a property of separation. But that's the answer. This is an answer, but I like much more the other answer. Faces separable. This is, for me, is absolutely the end of the matter. Here is a question of separation. Then we introduce this separation T0 star space. A space has a star properties of separation. If there is a family of open sets such that for x different than y, you always have a collection such that x, if x is in one of the set of the collection, y is not. If y is in one of the set of the collection, the other one is not. The star is the family of sets of the collection which contains the point. Okay? This is the definition. Then this is a topological concept. Indeed, anyone who opened the set theoretical topology handbook, big book of 19s, and go to Negroponte's or Negroponte's, for instance, or I don't remember now, Grunhey. Then there is explained very well this star property. Not this property, things which are related with that. We call it a star property this because we didn't have enough imagination to say a different way. The reality is that the star property should be Orihuela property. This I can say also because it's time for saying these things, for me at least. Okay, so for a family of subsets, we define this star and we say that a family T0 star if the family with functions, if the family of sets positives defined with the functions separates in this sense. So this is a separation property. Okay? Grunhey compact spaces have this property and this is between Grunhey compact and fragmentable compact. This is a property behind this. Okay? Between them. Theorem for strictly convex renorming. A normal space, the norm inside space, admit a lower semi-continuous strictly convex norm if and only if there are families of lower semi-continuous quasi-convex, say convex, it's the same, convex functions defined on S such that Gn T star 0 separates the point. Quasi-convex means the set less or equal than 0 is convex. The truncated of a convex function is a quasi-convex function. So, but right convex is the same. The characterization is the same. This is a solution. But still, I don't have the feeling that this is a characterization completely topological for the weak star topology. What happened with the Bing-Nagata-Smirnov theorem for the LUR case. The Bing-Nagata-Smirnov theorem for the LUR case says that we have a LUR norm if and only if we have a sigma discrete basis, which is the metrizability, but the sigma discreteness is also slicely isolated. Slicely isolated in the sense that they are disjoint, and every point has a slice that meets only one member of the family. This is exactly what it means. But okay, it's another one. Slicing with finite Hausdorff measure. This is the same spirit as I told before. Maybe have a look at the corollary, because it's instructive in the sense that how I measure the size here. Here I measure the size with sets which are Hausdorff null, finite dimensional Hausdorff measure 0. Means that this is a theorem of this mathematician from Sevilla, which is so good in Banach Spaces and application of the set theoretic work in Banach Spaces. I don't remember the name at the moment. Arias de Reina. Arias de Reina. This is the characterization. But have a look. This is the way of measure the complexity and the size of the slice. Main result, Banach space, enormous subspace, has an equivalent lower semi-continuous LUR norm if and only if there is again a sequence such that for any point x and any epsilon there is an open half space such that the slice is inside an epsilon neighborhood of a separable piece. Now a question for everybody. This is separable Banach spaces or is not separable Banach spaces? That's the victory. I'm saying very strong things. Today I'm saying very, very strong things. That's the matter, okay? Corollary, the Banach space that has a LUR norm if and only if there is another one with separable identity phases. It's a corollary of the former one. Trojansky did the matter with denting points, and the proof used the martingale index in order to arrive to the proof. It's in the book. Here there is no martingale, there is no index, there is simply an equivalent norm with separable denting phases. The proofs, okay, the proofs needs lemmas like this one, in which you go through the LUR condition, quadratic form goes to 0, to find approximation of xn and x0 for n big enough. So, and here is the proof for the case in which the slice is controlled by a finite Jordan content. We also have the same with Kuratowski index. Finite correspond to Kuratowski index. Kuratowski index was done by Trojansky with martingales, and we did later without martingales, with another approach. Now it's a different proof, completely different. The same, but now the slices are epsilon far, epsilon near of a perfect polysubset. A polysubset. perfect. Make combination, linear combination is perfect. There is no insulting points. So if you have this, again, we have the same theorem. If I have a Banach space, and for every epsilon and every x in the sphere, there is a half space such that the slice is covered with contour remain sets of diameter less than epsilon, then it admits an equivalent lower semi-continuous and locally uniformly rotor norm. This is something that I said even before. So, but this is the statement of the theorem just now. We can glue all the separable pieces. I'm not going to enter in these details. I simply go to the end. And before the end, let me just these things with the press down the faces. Press down faces means exactly that. I have a face. A minus delta is press down. B minus delta is press down. The theorem is Banach space and norm inside a space, blah, blah, blah. If I have a family of closed separable faces such that they are delta disjoint for some delta, then I have Lurer normability on this. And even if I have countably many families. So this is a very, very strong result. In a Banach space, as that the identity mapping is sigma continuous, for instance, in the descriptive space that began the K-analytic space of Talagram, for a family of separable compact faces, I have a local uniformly rotor norm on the union. And then the other day was a talk in which, I don't remember the name, but there was a guy constructing it's a paper with Peter Kayer, and they construct norm Lure on a dense subset. Here, with biotonal system. Here they are in full generality. A Banach space descriptive admits an equivalent strictly convex norm, which is also Lure on a dense subset. This is exactly the case of the other day, but in full generality. Let me a normal space with a norm in subspace, then admits an equivalent rotor norm if and only if it has another one with closed norm separable. This is the answer to Lindenstrauss, as I said before. But this is the theorem. And finally, the answer to Richard Smith. In a dual space, A star admits a dual rotor norm if and only if the dual ball has the property that I call Orihuela now, but was called a star. Okay? And a dual Banach space with dual Banach spaces which are weak star homeomorphic. Weak star homeomorphic. One is strictly convexificable if and only if the other one. That's wonderful. Thank you very much for your attention.